These are our solutions for review assignment 2.14. Some repetition from previous units to make sure we remember everything about limits. In our true-false, first we're asked whether it's possible to intersect vertical asymptotes. It is not. That is false. Second, is it possible to intersect horizontal asymptotes? That would be true. So let me quickly sketch a rational function that you might remember seeing. Rational functions that look like this, for example. A pretty rough sketch, but you can see that in the center of the graph we sometimes do cross the horizontal asymptotes. If the degree of the numerator is less than the degree of the denominator, then it approaches zero. That is true whenever the denominator of a fraction grows faster. Then its limit will go to zero. To find the domain of a square root function, we know that our domain has to be setting the radicand at least equal to 0. So this is the correct domain in number 4. In number 5, if f is continuous over the closed interval from p to q and r is an element of, that's what that symbol is as a reminder, if r is an element of the open interval, so in other words r falls somewhere between p and q, then is the limit of f as x goes to r equal to f of r. Well, continuity guarantees that there is a limit. The definition of continuity requires that there is a limit, and it requires that there's no pop point. So not only does the limit exist, but we cannot have a hole in the graph. So f of r can be found by direct substitution if our graph is continuous. Question 6, if the left-hand limit as we approach 5 is equal to 11, and the right-hand limit as we approach 5 is equal to 11, then the overall limit equals 11. That is our definition of a limit. So true by definition. In number 7, as x approaches infinity, the limit is 1. That's our right end behavior. So there's a horizontal asymptote on the right end. And as x approaches negative infinity, we approach 1. So on the left side, there's a horizontal asymptote. So this is the wrong conclusion. We know that y equals 1 is a horizontal asymptote. So we want to make sure we don't mix that up. If functions f and g are each continuous, is the limit of the sum? Does the limit of the sum exist? That is true by our limit laws, and we don't have to worry about division by 0, so that is always true. As opposed to question 9, because two functions are continuous, does the limit of the quotient always exist? Well, we could have the limit of f individually and the limit of g individually, but the problem is that the limit of g might be 0, so we have to avoid 0 in the denominator. So it might be true, but if the limit of g of x happens to be 0, then this limit law doesn't work. So that would be false in some cases. Avoid division by 0. Number 10, we've got a rational function. Notice this is an even function. It has symmetry to the y-axis. As we approach 0 from the left side, does the limit go to infinity? And whether we put in a positive or a negative, the numerator is always 7, so it's positive, and the denominator is squared, so it is always positive. So we know this graph has a vertical asymptote and a horizontal asymptote, and it is even. So it's going to look something like this. So this does go to infinity on both sides of 0. Question 11 is about the horizontal asymptote as x goes to negative infinity. When the denominator has a higher power, the denominator grows faster, so the value of this fraction, if we put in negative 1,000 here, will be 7 over a very large denominator. So it does go to 0, so that is true. In question 12, we have the limit of a square root. Well, we have a domain issue here. 3x squared minus 7 has to be at least 0. So let's make clear here that the absolute value of x has to be bigger than the square root of 7/3. Remember how you would have graphed that in algebra. Now, now I guess we should get used to. Ignore my tablet keeps erasing. If I go over the top, remember that instead of those solid circles, you can also use these square bracket endpoints. So there's our domain. Well, our limit laws says that the limit of a root can be the root of the limit. And then if we took the limit of each of the terms inside, so let's follow the limit laws here. So the limit of the first term, notice what we did. We moved the 3 outside the limit. And then we did the limit first, and then we squared it. So that is just a succession of our limit laws. So far so good. And the second part would be the limit as x goes to a of a constant. Well, the limit of a constant is just a constant. So we've applied the limit laws correctly. So while there is a domain issue, that might have been a more interesting question. Is this limit always defined? No, it's only defined when absolute value of x is greater than the square root of 7/3. However, are these two things equivalent to each other? When the first one is undefined, so is the second one. So I guess the question of whether they're equivalent would be true. 13, does it have a removable discontinuity? No, it has a vertical asymptote, an infinite discontinuity. So this would be false. 14, to find an x-intercept, we need to set y equal to 0. So when is a fraction equal to 0? A fraction is equal to 0 when the numerator is equal to 0. So this would not be our x-intercept. That would be false. And I kind of moved this badly. Let me put the y equals down here. So do we have a horizontal asymptote at y equals -1/2? No, our horizontal asymptote when the degrees are equal comes from the ratio of the leading coefficients. So our horizontal asymptote here would be at y equals 1. So that is also false. All right, let's see about 16. I think some of these look familiar. Point P, we need to find the y coordinate, and point Q, we need to find the y coordinate. And then we'll be able to find the equation of the line. Secant is just a line that passes through 2 points of a function. So when we put -1 into our function, we get 6. When we put 2 into our function, we have 9. So let's find our slope. And of course, you don't have to show this on your paper. You can do this work. 3/3 is 1. And now we go to point slope formula. Using either one of the 2 points, you'll get the same result either way. X minus a -1 becomes +1. In a free response question, you can leave it in point slope form. If it were multiple choice, you might need to rearrange it into its slope intercept form, but either answer is acceptable here. 17, let's find our elapsed time and our elapsed distance. So we're going 100 miles at 50 miles per hour. That would take 2 hours. And then we're traveling 30 miles at a speed of 60 miles per hour. That would take another half hour. So our total time would be 5/2 hours, or 2.5 if you prefer decimal form. And our total distance, we traveled 100 miles and 30 miles. So 130 miles in 5/2 hours. I would multiply by the reciprocal first, and then I would divide by 5, but you might do that in a little different order. But make sure that your answer is labeled in correct units. This is our average velocity. Does not mean we were always traveling 52 miles per hour. but at least once we were. Sometimes we were traveling slower, sometimes faster perhaps, but this is our average velocity, the slope of a secant line. All right, looking at our graph, and I see I have an issue here just when I transferred Microsoft Word. Let me put that hole back here. I think it drifted, so let's put a hole in the graph back where I think it was on your handout. All right, as we approach 2 from the left side, our limit approaches a y-coordinate of 2. As we approach 2 from the right side, we approach 0. So since the left and the right hand limits do not agree, there's no overall limit. And of course we know that we will call that a jump discontinuity. I can already see that's the question in 24. In 21, we're doing the limit as we approach 4 from the left side. Well, we get close to a y-coordinate of 3. And as we approach 4 from the right side, we approach 3. So there is an overall limit, even though it is a removable discontinuity. And question 26 is about our special case here. What's happening at 0? Well, as we approach 0 from the left-hand side, we have a left-hand limit that approaches -1. As we approach from the right-hand side, we approach -2, but notice there you have an open endpoint. So this was our special case where we said there is a limit. It is continuous from the left side, but it's called discontinuous from the right side. So just a little bit of vocabulary there. So if it can get right up to the closed endpoint. So we would say it is continuous from the left, but discontinuous at the right. It does not have an overall limit. It has a jump discontinuity. So A would describe this the best. All right. When we have limit questions, our first instinct is to always do direct substitution. If we put 1 in for x, we get 0 over 0. That does not mean that the limit doesn't exist. So a little bit of algebra might solve our problem. So let's see, there might be a removable discontinuity, and it gets its name because we can remove the 0 over 0 case. So the difference of cubes, factors, and now the factor that causes the hole in the graph has canceled, so now we can find our limit by plugging the hole. Put 1 in for x, and we'll get our limit of 1/3. In 28, if we did direct substitution, putting 1 in there, our numerator would be 3 minus 3, and our denominator would be 1 minus 1. So again, it's that 0 over 0 case. So let's see if it's a removable discontinuity. And a hint to make your factoring of the numerator faster is be suspicious that perhaps one of the factors will be an x minus 1. Isn't always going to be the case, but I think you're suspicious. That's how math problems are written. So double check FOIL to make sure you get back to the original there so that your factors are correct. But we do have a removable discontinuity. So we've solved the problem, and we can put 1 in for x, and we will come up with 5 over 1. So we get a limit of 5. In 29, rational functions near a vertical asymptote. Well, this is not written as one ratio. So let's clean up the algebra first. If we were going anywhere other than -2, but -2 causes the denominators to be 0. So we should put this together as a rational function. So let's multiply the first fraction by x plus 2 in order to get a common denominator. And again, I'm not suggesting that you have to show all of these steps individually. You can skip as many steps as you wish. So our numerator, oh, sorry, I guess I was multiplying by x minus 2. So our numerator is now x plus 2. And our denominator, common denominator, is x squared minus 4. So let's factor it. And now we can see there's a hole in the graph. We've canceled the common factor, and then, did I cancel the wrong factor? No, our limit here is going to -2. I just forgot to write my negative sign there. All right, so we put -2 in to our leftover factor, and we'll come up with -1/4 as our limit. So remember what you've just found out. You found out that there's a hole in the graph when the x-coordinate is -2 and the y-coordinate is -1/4. So the limit is the y-coordinate where the hole in the graph occurs. Question 30, if I just did direct substitution, I'd get 0/0. This is a complex fraction, so some algebra, I hope, seems obvious. How do you simplify a complex fraction? We multiply the numerator and the denominator by the common denominator of any fractions that you see here. So if I distribute in the numerator, the first term will be a 1, and the second term will be a -x². And in the denominator, you could distribute, but do you think you're going to factor right away in the next step? So instead of distributing, I'll just leave it in factored form. So I can see that when I put 1 in, we're going to have a removable discontinuity, but be careful about your factoring here. Before I factor this, I think I might prefer to change the signs. Factor out a -1, and then it would be x² minus 1. Of course, that's not the only way to think of this, but it might be the best way to avoid making a negative error. So now our x minus 1 is our common factor where the hole occurs, and now we can do our direct substitution, put 1 in for the x, and our numerator will be -1 times 2, and our denominator will be 1. So if my arithmetic is correct, I believe we have -2. So again, what you're doing every single time there's a common factor is a removable discontinuity. When x is equal to 1, the hole in the graph would have a y-coordinate of -2. In 31, we have the limit of a composite function. Well, I'm not sure what exactly we want to do with that, but there's no division by 0 problem. At pi/2, we know we can only do logarithms of positives, so we know that the domain of this, when does sine have a positive result, that would be from 0 to pi, and then it would have a discontinuity, and then it could go from 2 pi to 3 pi. So there would be various pieces of this graph. We're only interested in what happens at pi/2. So pi/2 in our domain from 0 to 2 pi, and then from 0 to 1 pi. And then we could go again from 2 pi to 3 pi. So we know that pi/2 is in one of the defined parts of this function. So I think we could do direct substitution here. So we know the sine of pi/2. The sine of pi/2 happens to be 1, and the natural log of 1, as we put pi/2 in here, doesn't matter. There's no more variable. The natural log would be 0. So you're saying e to what power produces 1. So that's where I'm coming up with 0. I'm doing the logarithm question. So we're in a continuous section of the graph. So pi/2 is defined. It's in the domain. So I just did direct substitution. And then I did the sine first, and then I did the log second. All right, what about this function? We're looking for a horizontal asymptote. The denominator has the higher degree. You might right away now be catching, though, that this has a common factor. So these are going to cancel. Now that doesn't change the result here, that this is going to, as we go to infinity, the denominator has the higher power, so the denominator is growing faster. So it's going to approach 0. So it's good that you notice that there's a removable discontinuity, but that factor, that fraction is still going to approach 0. 33, we need to rationalize by the conjugate to avoid 0 over 0. Again, notice if we had just tried plugging 9 in, we would have had 0 over 0. But we are getting used to the idea that these are written so that, again, it'll have a removable discontinuity. So the x minus 9 factor cancels. And now we can fill in the hole. Put 9 into our result here, and we will come up with a limit of 1/6. And our question 34 is another horizontal asymptote. Notice it's written out of order. The leading terms are 4x squared and negative 2x squared. As x goes to infinity, these other terms will become negligible. The highest power terms are going to grow so much more quickly than the other terms when x is very large. When the degrees are equal, we take the ratio of the leading coefficients, so 4 divided by negative 2. So our horizontal asymptote, in other words, will be at y equals negative 2. That's the question we're looking for here. In 35, remember that our sine and cosine waves have boundaries, but those positive 1 and negative 1 lines are not asymptotes. That's the reason this question keeps coming up. Students sometimes want to say that it's plus and minus 1. Those are not asymptotes, though. The graph never gets closer and closer to it, so the limit does not exist. In 36A, we're on the right end behavior. So let's think what happens when our exponent becomes incredibly large. These two terms are going to be very large values, and this term is going to be negligible. So we have e to some very large power over itself, so this is going to go to 1. Even though those two terms get incredibly large, they get incredibly large at the same rate. So their ratio is equal to 1. As opposed to 36b, what's happening when our exponents are very negative? So when our exponent is very negative, so you're picturing a negative exponent, would flip to the denominator and we double it. So this fraction is going to go to 0. So these two fractions go to 0. These two fractions go to 0. So what would be left? What would be left if we ignore those two terms? Our numerator would be 0 and our denominator would be 1. So this is going to go to 0. And here we just have our e to the x function, of course, rises on the right side. Our e to the negative x function, remember that e to the negative x is the same as 1 over e to the x. So when the negative is with the x, it is a horizontal reflection. On the positive side, it will go to 0. So you've seen most of these questions before. In question 38, here's our sine of a glob over the glob as the glob goes to 0. So this one, if you tried direct substitution, the sine of 0 is 0. So you get 0 over 0 problem, and we have no algebra to solve this, but we do have a theorem, and we've now in class proved that theorem by using the sandwich theorem. So we now accept that the limit of sine of a glob over a glob goes to 1 as the glob goes to 0. So our problem in B is that we have a 7x glob in the numerator, and we would like to have a 7x glob in the denominator. So you might not want to show this work each time, But again, I'm going to show you that we're using our limit law to bring the constant 1/2 out of the function. And then, can I turn this into a 7x as I would wish? Well, I can divide by 7 only if I also multiply by 7. And that 7 I can choose to bring out in front. So now I can write this as 7/2, the limit as x goes to 0 of sine of a glob over the glob. And sure enough, when x goes to 0, the glob is going to 0. So this is our theorem. So we have 7/2 times 1. So of course this goes to 7/2. If it were a multiple choice question, you say, I remember doing this, I know the answer is going to be 7/2, that would be fine. Okay, I'm going to stop this video and continue in a second video.